recording. Okay, yes. Oh, yes, James, I saw, but I didn't get a chance to look at it yet. All right, so I will check it after class. Okay. So, okay, great. So at this time we're recording, so you can put in your name so that we have your record for attendance. My guess is that we won't go all the way until 6 o'clock today. We'll probably finish between 5 and 5:30. So I'm not sure I'm going to have the stamina to go until 6 o'clock. Okay. So, okay, good. But welcome everybody. It's as always, it's great to see you all. Good. And yeah, you can start typing in your name if you need you can start typing in your name. I need to check one quick thing before we start. Give me a second. Um, one quick thing before we start. What is this? Let's see, 2025. Here we are. Okay. All right. Okay. All right, so why don't we get started? I'm just going to recall a few of these things that we did last week. So remember the last few weeks we've been talking about these antiderivatives, right? And so if we have a function which we call little f, then a function capital F is called an antiderivative if the derivative of capital F is equal to little f. And we've also seen that if you have one antiderivative of some function little f, then you can add a constant to it, and that's always going to also be an antiderivative, right? So, example of this is that, x squared is an antiderivative of 2x, but x squared plus 5 is also an antiderivative of 2x. Right? So we have, you can always add a constant, and that gives you all of these antiderivatives. And so we saw some applications of antiderivatives yesterday, which we'll go over a little bit in the homework questions today. So the applications had to do with physics and also had to do with areas. So let's review what they were. So remember in physics, what was the relationship between velocity and distance and anti-differentiation? Well, let's say that we have a velocity function given by v of t, then we saw that the position function s of t is an antiderivative of v of t, right? This is the same thing as saying that the velocity function is the derivative of the position function. It's the rate of change. And furthermore, if our velocity function is always positive, meaning we're going in one direction, then the distance traveled from time A to time B is s of b minus s of a, which is also the area under the graph of v of t from t equals a to t equals b. So what's the picture here? The picture is I have some graph. This is my time axis, and this is my velocity axis. I have some time A and some time B, and maybe my velocity changes. This is the graph of, y equals v of t. And then if I want the total distance traveled, I look at this area under this graph between A and B, and this area equals the total distance traveled. Right? And that area, that total distance traveled, is actually s of b minus s of a, where s can be any antiderivative of v. Okay, so we saw this right in some basic cases where the velocity was constant. This was just saying that distance is equal to rate times time as a rectangle, but actually it works for any velocity function at all. So if you have a velocity graph, then the area under that graph is the total distance that you travel. Okay. And that area is exactly, you can't see the function s on this graph, but the reason that this worked is because that area is given by s of b minus s of a. Okay. Um, good. So with this being in mind, we have the first homework exercise, which just says the velocity graph of a braking car is shown below. I'll just try to copy it. Let me see if I actually remember how to copy this graph. How do I? At some point, I should learn how to actually use this program. There's plenty of ways that you can do cutting and pasting and stuff like this. Let me see if I do this. Will that, can I cut and paste that? No. I need to learn how to actually do this. Okay, well, I'm just going to try to recopy the graph. Okay, oh no, that's not what I want. We have, so 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. This is time in seconds. And then I have velocity. So 20, 40, 60. This is velocity in feet per second. And then we have this graph, which looks something like this. So let me draw it in green. So it goes something like this. And then I'm just going to copy it down. So, and then what's the next part? Then down like this. Okay. So this is how a car brakes. Okay, and so the estimate, so this gives the velocity. So the green line is the graph of the velocity function, right? And the question is just to estimate roughly how far does the car travel while it's braking. Okay, so we basically just need to estimate the area under this curve. So does anybody have kind of an estimate for how we do this?
Yes,
Yes,
Talaba.
Enoch?
Yes.
Yep.
To estimate the area under the curve, we either use integration by using the area, or another way we can use it as a slope,
Hmm.
which which we will have change in velocity and change in the time,
Hmm.
change in velocity, all divided by change in time. But the velocity we can take point 2 and point 1 from the graph. Then
Hmm.
the time we also take point 1 and point 2 from the graph, beginning at some initial stage.
Hmm.
So, for example, we can make a point between 20 and 60 on the velocity.
Yeah,
Then on a we made a point between 1 and 6.
right. Yeah, so I think the area is going to be the easier way to do this, right?
Yes,
So your first method. So we basically just need to estimate how much area there is under this graph, right? And so more or less we're counting boxes, right? So I mean we can just start marking these boxes out, right? And we've got one box, second box, third box. We have maybe most of a fourth box. We lose a little bit up here in this corner, but we have almost the whole box. And then maybe, so that's four boxes so far, right? And then maybe these two together are about one box total. Maybe I'll draw a little X here. And then these two together are maybe a little bit more than a box. And maybe with these little two extra things, I would estimate that this is about 1.5 boxes between these two. Yeah, the total area, but only the area under the green line, right? Because the car is starting at about 70 feet per second, and then it's slowing down to zero while it brakes. Yeah, so it's just the total area. That's all that we need. That's the amount that the car travels is the total area, right? That's what we saw below. The total distance traveled is the area under the curve, right? So over here it looks like we got about 5 boxes, and then I would estimate in total, I would estimate that I've got about in total that it's about 6.5 boxes, right? I would guess this is about 6.5 boxes in total, right? And so 6.5 boxes, yeah. So James is 120, which is a reasonable estimate. if it's 6.5 boxes, right, each box is equal to 20 feet per second times 1 second, right, which is 20 feet. So total, my guess would be 6.5 boxes times 20 feet per box, which would come out to be 130 feet. But,
That'll
if
be
you
the
think it looks more like 6 boxes, that's very reasonable also. I would think maybe 6.5, but yeah, 6 is okay also. Okay, so that would be my guess for how much the car travels approximately. Okay. Yeah, that's close enough. I mean, of course, you can't be that precise because this graph is drawn kind of crudely. So, as precise as you want to be, the extra digits of precision are maybe not so useful. But roughly, 120 feet, 130 feet, something like that. Okay. Any questions here? Okay. Um, okay, good. Yeah, so this is really just counting the area. Okay, and we know that the area under the curve tells us the distance traveled. Okay. Okay, so let's recall that we can also do this with anti-differentiation, right? I mean, in this example, we can't use anti-differentiation because I didn't give you any formulas for the function. I just drew something. So you have to just calculate the area, right? But in general, if you have a formula, if you have a mathematical formula, then you can hope to calculate these areas using what's called anti-differentiation. So specifically, the area, if I have a curve y equals f of x and I want to calculate the area under that curve from x equals a to x equals b, then this is given by this very important formula, f of b minus f of a, where a and b are the bounds there, and f is any antiderivative of little f, right? And this is sometimes called a definite integral. And so in particular, if f is a function that has an antiderivative capital F, then we use this notation, which you read as integral from a to b of f of x dx, that this is just the notation that means capital F of b minus capital F of a. Yes, it's possible to use Riemann sums, but we're not going to touch that right now. Yes, but we're not going to uh, that. Okay, so great. So for us, we have this antiderivative that allows us to calculate these areas under the curve. So, for instance, we have this next problem, which is to evaluate the integral from 1 to 2 of x times 1 minus x squared dx, right? So all this means is we need to calculate an antiderivative of this function, okay? And then evaluate it at 2 and evaluate it at 1 and subtract. Right. So the first thing is we first want to find an antiderivative, which I'll call f of x, of x times 1 minus x squared. Okay. Okay. So, all right, great. So now the problem is this form is not a great form to calculate an antiderivative, right? Because it's kind of complicated. It's not easy to just guess what's a function going to be whose derivative is this. So what we need to do in order to calculate an antiderivative is expand this out and simplify it first, right? So we need to know that x times 1 minus x squared, well, that's equal to x times, well, we can expand out 1 minus x squared, right, as 1 minus 2x plus x squared, right? That's 1 minus x squared. Um, And then if we multiply the x through by everything, then we end up getting x minus 2x squared plus x cubed, right? So we haven't done anything yet. We've just rewritten this function as x minus 2x squared plus x cubed, right? So James gives 7/12 as the answer. Let's see. So now we need to find an antiderivative. And for this, we can use the power rule, which I'll recall over here. Power rule, remember the antiderivative of x to the n is 1 over n plus 1, x to the n plus 1, at least whenever n is not equal to minus 1. Okay? So for this antiderivative, we know that the antiderivative of x is 1/2 x squared. X squared is 1/3 x cubed, but we have a 2, so it's minus 2 times 1/3 x cubed. And then the antiderivative of x cubed is 1/4 x to the fourth. And now we have a notation that I'm going to introduce, which is, well, right, we want to do evaluate this at 2 and at 1. So the notation that people use is you write a line here, and then you write a little 1, and then you write a 2 here. This means evaluate at 2 and at 1, and then subtract. Okay, that's what this notation means over here. So we have to evaluate this at 2 and then at 1 and subtract. So we plug in 2. Sorry, what do we get when we plug in 2 over here? We have 1/2 times 2 squared minus 2/3 times 2 cubed plus 1/4 times 2 to the fourth. And then minus, we do the same thing at 1. 1/2 times 1 squared minus 2/3 times 1 cubed plus 1/4 times 1 to the fourth. Okay. So this is what we have for these two pieces over here, right? This here is f of 2, and this here is f of 1. Okay. And so now the rest is just arithmetic. We have to figure that out. So 1/2 times 2 squared is 2, minus 2/3 times 2 cubed is going to be 16/3, plus 1/4 times 2 to the fourth is going to be 4, minus 1/2 times 1 squared is 1/2, then minus 2/3 times 1 cubed is 2/3, and then plus 1/4 1 to the fourth is 1/4. And now if we simplify this, this is going to give us what? It's 6 minus 16/3 minus 1/2 plus 2/3 minus 1/4. And that becomes, let's see, this is 6 minus 14/3 minus 3/4. So, right, so let's see. So this is 6 minus 14/3 minus 3/4. And I guess we'll need to get a common denominator of 12 to do that. So let me write this on another page. So 6 minus 14/3 minus 3/4. We can get a common denominator of 12. So that's 72 over 12 minus 56 over 12 minus 9 over 12. And that comes out to be exactly as James said, 7 over 12. Okay, so that's going to be the final answer there. Okay, so this is all just doing common denominators of 12 to get every one of these terms as a fraction with a denominator of 12. Okay, so this gives us 7/12 here. Is that okay? Maybe I'll go back to this page so we can see what happens. So, all that you're doing is simplifying it to the point where you can use the power rule to compute an antiderivative, right? Yes, correct. Correct, James. Um, okay, so that's how this homework exercise works. Okay, once you can compute the antiderivative, you evaluate it at 2, evaluate it at 1, and subtract. So if you had this as your velocity function, then from time 1 until time 2, the distance that you travel would be 7/12 of a unit. Okay, great. Okay. So exercise three, let's say we have a runner, and at half-second snapshots, we have the runner's velocity. So at time zero, the runner's starting from rest. And then in half a second, the runner is running at 6.2 feet per second. At 1 second, 10.8 feet per second. And so on up until 3 seconds, the runner is running at 20.2 feet per second. And so the question is, what is a reasonable approximation for the total distance that the runner travels in the first 3 seconds? Uh, Again, we don't know the exact distance, right? Because in order to know the exact distance, we would have to know the runner's velocity at all times, not just at these snapshots. Right? If we knew all times, then we could draw the graph and we could calculate the area under the graph, and that would be the total distance the runner travels, right? But we don't know that, right? We don't know that. We only know these snapshots. So the best, I mean, so, we have a few different things that we could try, right? But basically, the best thing that we can do is just assume that maybe, here's one assumption that you could do. Maybe assume that in each half-second interval, the runner averages the average, sorry, averages the average of the beginning and ending speeds. Okay, so we could make that's a pretty reasonable assumption. You could also, right, so the time interval, as James says, exactly is 0.5 seconds. So, and so we have six different intervals, right? We have 0 to 0.5, 0.5 to 1.0, 1.0 to 1.5, 1.5 to 2.0, 2.0 to 2.5, and 2.5 to 3.0. So we can think six time intervals, each zero point 0.5 seconds long, right? Okay. So then maybe we'll guess first interval, maybe the average speed should be approximately 0 plus 6.2 over 2, which would be 3.1, right? I'm taking the average of the speed at the beginning and the speed at the end and call that the average. So on average, maybe we can guess that the speed is 3.1 during that first time interval. Second interval, average speed should be approximately 6.2 plus 10.8 over 2. That's going to be 8.5. Right. I mean, this is all feet per second, but I'm not going to keep writing feet per second. Okay. And so third interval, average speed. At this point, I won't write out the computation. So 10.8 plus 14.9 over 2, that's 25.7. So that's going to be about 12.85. The fourth interval, average speed, it's 14.9 plus 18.1. That's 33. So the average speed is equal to 16.5. In the fifth interval, we have 18.1 plus 19.4 divided by 2. So the average speed is 18.75. Uh, and lastly, in the sixth interval, the average speed is the average of 19.4 and 20.2, which is 19.8. Okay, so I didn't write down all the calculations, but they're all done the exact same way as these first two. Right, so the total distance in that first 3 seconds is approximately equal to what? Well, if these are the average speeds over each of the intervals, and the intervals are all about half a second, then how do we calculate the total distance? Anyone want to say how we do this? Well, remember, distance is equal to rate times time, right? So if we have an average speed and each interval is zero point 0.5 seconds, then the distance, we do integrate, but we don't need to integrate, right? Because we don't actually have a velocity function, right? So we're not going to be able to take an antiderivative. At this point, the best we can do is just estimate we have the average speed over the first interval, for instance, is 3.1 feet per second. If we multiply it by the time, which is half a second, then that's how far the runner's gone in that first interval. And how far does the runner go in the first 3 seconds? It should be the sum of the distance traveled in all six of the intervals. So the total distance here should be approximately 0.5 times 3.1 plus 0.5 times 8.5 plus all the way up to 0.5 times 19.8. Okay, 238.5. Let's see. So this is 0.5. I can pull the 0.5 out because that's going everywhere. I've got 3.1 plus 8.5 plus 12.85 plus 16.5 plus 18.75 plus 19.8. And let me do this on the calculator. So 0.5 times 3.1 plus 8.5 plus 12.85 plus 16.5 plus 18.75 plus 19.8. I'm getting 39.75 feet. I'm getting 39.75 feet. Is that okay? Okay, we just do the average speed on each interval and then add it all. Now, if you wanted to, you could use a different approximation. You could just use the final speed as as an approximation for how fast the runner's going. So you could say the final speed is 6.2 for half a second, and then 10.8 for half a second, and so on up to 20.2 for half a second. On that case, you would get a slightly higher interval. Okay. I'm sorry for the bad network for everybody.
Hello.
Hello, Rash.
We're not taking a 3 second, right?
Well, in total, it's 3 seconds,
Okay, okay.
right? But that 3 seconds is divided into six half seconds.
Okay, right. I think that make I got that far.
Yeah.
This guy
Hello.
that's the reason.
Oh, okay. That makes sense. Yeah, no, we don't
Yeah.
multiply by
Yeah.
the three.
Later.
The 3 seconds is already there. Prince, you have a question?
Yeah. 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 I have a concern here.
Mm-hmm.
Yeah. What more of we are only entitled to look at the velocity interval. One more of a time, which
Mm-hmm.
is the second. Because I not see any application from the time interval. Only the velocity.
Well, here's the
So
chart here
the
has the
time
time.
interval it doesn't matter or what.
Well, no, the time matters. So this is the time.
Uh,
So this T stands for time. The T is time. So this is at 0 seconds, 0.5 seconds, 1 second, 1.5 seconds, 2 seconds, 2.5 seconds, and 3 seconds. So this is like imagine a stopwatch that stops at each after you there's at the beginning the runner's not moving. Half a second later, this is the runner's velocity. 1 second later, this is the runner's velocity. 1.5 seconds later, this is the runner's velocity, and so on. So it's giving you a snapshot of the velocity after zero point 0.5 seconds, after 1 second, after 1.5 seconds, after 2 seconds, after 2.5 seconds, and after 3 seconds. So what we're doing is each of these intervals is a half second long. So for each of these intervals, let's say in the second interval, that's between 0.5 seconds and 1 second. So the runner's averaging about 8.5 feet per second at that interval. So during that interval, how much ground does the runner cover? Well, it's half a second times 8.5 feet per second. So the runner's going to cover 4.25 feet. So yeah, so this final answer is our approximation for the distance the runner travels in the first 3 seconds. Does this answer the
Oh,
question?
okay, okay. Thank you.
Is that okay? Okay. Other questions? Okay. All right. So let's move on to some new stuff. So today we're going to talk about exponentials and logarithms. Okay. So let's review what it means to take the exponential. So remember that when we have a fractional exponent, like if I have some number a and I raise it to the b over c, that means I raise it to the b and then I take the cth root of that, right? So, right, my example here, right, is that if I have something like 8 to the 2/3, this is equal to the cube root of 8 squared, which is equal to the cube root of 64, which is equal to 4, right? So 8 to the 2/3 equals 4. All right. And so we can define exponentiation whenever we have a rational exponent like this. And to using continuity, we can extend this definition to define a to the x for any real number x. So in fact, we can have a graph of a function like y equals 2 to the x, and you can graph it. So if this is, 1, well, 2 to the 0 is equal to 1. And then, the exponential function looks kind of like this. This is usually what the graph of an exponential function tends to look like. You can imagine this is y equals 2 to the x. Okay. Okay, this is what the graph of an exponential function looks like. Okay, and we have our basic laws of exponents, which are that if you have a to the x plus y, that equals a to the x plus a to the y. That's fine, no matter what your x and y are. And then this other law, which is that a to the x to the y is equal to a to the xy. These are the two major laws of exponents. Okay, there's a third law, which is basically the same as the previous law, but a to the x minus y equals a to the x divided by a to the y. And in general, a to the minus x, this is more a definition than a law, is equal to 1 over a to the x. Okay, so these are your basic laws of exponents. Okay, so we have these exponential functions that are pretty important. They describe in particular exponential growth, which we'll have a class about a little bit later in the semester. Okay, so okay, so these laws of exponents, this should all be pretty familiar. Um, And so now the exponents are familiar. What might be a little bit less familiar, although we've covered it in earlier iterations of the class, is logarithms. So if you have the function a to the x, it has an inverse function called a logarithm. And the inverse function, we usually write f inverse of x, and this is written log to base a of x. So what this means is what power must a be raised to get x? Okay, so 2 to the fifth is 32. That means that log 2 of 32 is equal to 5. That's saying that you have to raise 2 to the fifth power in order to get 32. Okay? So this is what we mean by it. It's the inverse of exponentiation. It's not saying what is 2 to the fifth. It's saying what do I have to raise 2 to in order to get this in order to get this number, in order to get 32. And so that answer is 5. And more formally, I mean, this is a particular example, but more formally, what does it mean that logarithms and exponentials are inverses, right? It means that if I do one and then do the other, that I get back to where I start. So if I take a to the x and then I take the log to base a, then that gives me x, right? It kind of has to, right? Because this is saying what power do I raise a to get a to the x? Well, the answer is I raise a to the xth power in order to get a to the x, right? So the log base a of a to the x is always going to be x, and this could be for any numbers a and x. We always want a to be positive. And similarly, over here, you can do them in the reverse order. You can do log and then exponentiation, and that also is going to give you your basic function x, right? So here we have a to the, it's a little bit trickier to understand this, but we have that a to the log a of x equals x. What does this mean, right? Well, remember, log a of x is the power I need to raise a to in order to get x. The power I need to raise a to in order to get x. But this means, well, it's the power I need to raise a to. So if I raise a to this power to log a of x, then I get x, right? This number is literally defined as what exponent do I need to throw onto a in order to end up with x. Okay? So it turns out that logarithms have their own rules, so that are kind of the reverse of exponential rules. We're not going to use these very much, so I'm not going to spend a lot of time going over them. But let's just remember that the log to base a of xy equals the log a of x plus the log a of y, and the log to base a of x to the y is equal to y times the log to base a of x. Okay, these are rules of logarithms that you can go over if you want to at some point. Oh, by the way, I wanted to give you what is the chapter here, right? Everything here, by the way, is chapters 5.2 and 5.3 in the book. Okay, so we have these functions, exponentials and logarithms. This is not going to be a lesson on exponentials and logarithms, so if people want one, we can do one later. But what this is really going to be a lesson on is how do we do calculus with these functions? Okay, so I have done large units on exponentials and logarithms in earlier years of the program. Okay, but the point is we have these two types of functions. We have these exponential functions, a to the x, and we have this logarithm functions called log a to base x, log of x to base a. Okay. And so one question, so now there's going to be a special number we're going to talk about, which is called e. So it's just a number. It's equal to about 2.71828, so on. It's an irrational number, so the decimal expansion goes on forever. And one way that you can define it is by saying that e is the limit as x goes to infinity of 1 plus 1 over x raised to the x. Okay? So it turns out this has a unit, this has a limit, and imagine this with like a very large x, right? So what do we get, as an example, right? Let's say I take 1 plus 1 over 1,000 raised to the 1,000, right? That's not quite infinity, but it's getting close to there, right? So what is 1 plus 1 over 1,000 raised to the 1,000? Let me put that in. to the calculator, this is going to be 2.7169, roughly. So it's not quite the same as 2.7182, but it's getting closer. And then maybe I'll try what happens if I add another digit. Let's say I have 1 plus 1 over 10,000 raised to the 10,000. That turns out to be uh, 2.71814. And maybe I'll just do one more. 1 plus 1 over 100,000 raised to the 100,000. This turns out to be 2.71827, and so on. So you can see it's getting the larger I take my x, it's getting closer and closer to this number e. And so it turns out that as x goes to infinity, the limit of this is exactly e. Okay. Okay. Hi, Sanjay. Okay, so this is a number. It happens to be a very important number. It's Hi, Sanjay. How are you?
I'm good. Good to be back.
Good. Good to see you. So this turns out it's actually very important when calculating compound interest in a bank account, for instance. Not going to do that now, but this limit is kind of a very natural thing. And then E has this very important property, which I'm also not going to prove. But if you take the limit as h approaches 0 of e to the h minus 1 divided by h, that this is equal to 1, right? And let me just notice what happens if I just punch in 0. E to the 0 minus 1 over 0. This goes to, 0 over 0 indeterminate. And you might say, oh, well, then why not use L'Hospital's rule to figure this out? But the answer is you can't because you don't know how to take the derivative of e to the h. Yeah, this is the problem. Okay, so at some point you actually have to calculate this limit without using L'Hospital's rule, which is fairly hard. So I'm going to skip that. But for now, let's just use this as a fact. Okay, so the limit as h approaches 0 of e to the h minus 1 over h, I'm going to tell you as a fact that this limit is equal to 1. Okay, it's an indeterminate form, but it turns out that it's actually 1. Okay, and again, you can try this, right? What happens if we do a really small number? So what's e to the 0.0001 minus 1 divided by 0.0001? Let me just try this on the calculator. So e to the 0.0001 minus 1 divided by 0.0001. This turns out to be equal to 1.00005. Okay, and maybe I'll do one extra decimal place. 0.0001 minus 1 over 0.00001. This turns out to be 1.00005, right? And so on. Okay. So remember back when we did limits, one of the ways that you can try to experimentally figure out a limit is by just using tables of values, using values that approach 0. So here I can approach 0. I'll first punch in 0.0001, then 0.00001, and then I can throw in some more zeros, and what you'll see is that this limit is going to approach 1. Okay, so this is a pretty important formula. So I'm going to box it. Okay. Yes, it's the base of the natural logarithm, which we'll get to in a minute. Okay. So this is this number e. Okay. So now here's a question. So what is the derivative of e to the x? All right, now some people may know the answer, but let's actually calculate it, right? We're not going to be able to use any rules to do this, right? This is not going to be something we can calculate using the quotient rule or the product rule or the chain rule or the power rule or anything like that. This is a completely new type of function. It's not in any of those forms. So our only choice is to use the definition of the derivative, right? What that means is that the derivative of e to the x, remember by definition, this is the limit as h approaches 0 of e to the x plus h minus e to the x divided by h. Right? In general, right, f prime of x is equal to the limit as h approaches 0 of f of x plus, let me write this with some more space. Um, Reminder that f prime of x in general is the limit as h approaches 0 of f of x plus h minus f of x divided by h. That's our formula for the derivative. So here we f of x is e to the x. So we have e to the x plus h minus e to the x over h. But now we can use the rules of exponents. This is the limit as h approaches 0 of e to the x times e to the h minus e to the x over h. Right? Because this is the rule of exponents. When I add exponents, I multiply the exponentials. So e to the x plus h is e to the x times e to the h. Right? And now I can factor out an e to the x. That's equal to e to the x times the limit as h approaches 0 of what happens when I take out e to the x. I have e to the h. Here I had e to the x. That's just going to become 1. And then here I have this h. And we saw on the last page that this limit is equal to 1. So in the end, you just get e to the x. Okay, so e to the x is this kind of amazing function that satisfies that its derivative is itself. Okay, so the derivative of e to the x is e to the x. Okay, and it's calculated, and you do it by using this formula. Of course, you have to be able to evaluate this limit, which is not that easy. So you have to take it on faith for now that this is actually 1. Okay.
First principle.
Sorry,
The first principle, right?
sorry, say that again.
Hello?
Hello, yes, Rush?
The first principle we're applying, right?
Yeah, first principle. Exactly. Yeah. Yeah. Right. So I mean, yeah, somehow I mean, so Enoch, I see your comment, but the point is, yes, so it's the chain rule, right? But in order to apply the chain rule, you have to know the derivative of e to the x in the first place. So it's kind of circular reasoning. So this is how you calculate the derivative of e to the x based on first principles. Okay, and it turns out that it's going to be e to the x. Okay. Now give me 1 minute. I need to go get some water. I'll be right back. Okay, so the derivative of e to the x from this procedure we get is actually just e to the x again. Okay. Now, the inverse function of e to the x, so is a very special logarithm, which we call the natural logarithm. So the log of x to base e, remember, e is just some number. It's just 2.7, or it's about 2.7, right? Yeah, perfect, Rush. That's right. Exactly. Yeah, so if people want to see it in the chat. So this logarithm is important enough that it gets its own name. It's called ln of x. ln is equal to what's called natural logarithm. Okay. And so you can ask can we calculate the derivative of ln of x? Okay. Well, again, we don't have a rule that lets us calculate the derivative of ln of x, right? We don't have we can't use the product rule or the quotient rule or anything like that. But so we're going to do a little bit of a different approach. So you could try going from first principles also. But first principles to calculate the derivative of ln of x is actually pretty hard. So here's what we're going to do instead. Let's imagine we have the function y equals ln of x. Well, I claim that if we raise both sides to the e, what this tells us is that x equals e to the y. This is because logarithms and exponentiation are inverse functions, right? If I have y equals ln of x, then I can take e to the y is going to be equal to e to the ln of x. But what is this e to the ln of x? This is equal to e to the log e of x. And we've already seen that e to the log e of x is just x. Okay? So basically, e and natural log cancel each other out. Just like 2 and log to base 2 will cancel each other out, right? E is just a number, and this ln of x just means the log of x to that number. So when I raise e to the log e of x, they cancel out and they give me x. Okay, so what I have now is e to the y equals x. And I want, remember, y is ln of x here. So now I want to calculate dy dx. Okay. So now the trick here is to take the derivative of both sides with respect to x using the chain rule. Okay. So I have d dx of e to the y equals, and equals d dx of x, which in other words is saying that d dx of e to the ln of x is equal to d dx of x, right? Because, e to the ln of x is x, so their derivative should be the same. All right, well, let's see what we get here. Well, on the right-hand side, it's easy. The derivative of x is just 1, right? So I just get a 1 on the right-hand side. What about on the left-hand side? Well, we have the chain rule here, right? We know the derivative of e to the x is just e to the x. But now we have a composition of functions, right? It's e to the ln of x. So if you remember by the chain rule, what do we get? We get that the derivative of e to the something is just going to be e to that something times the derivative of the something. So in this case, the derivative of this using the chain rule is going to be e to the ln of x times the derivative of ln of x. Okay, so this is what you get when you take the derivative of the right-hand side, right? It's the derivative. If we have to do this using the chain rule, remember what this is. This is, maybe I'll write it in red. This is f of g of x, where here f of x equals e to the x, and g of x equals ln of x. So d dx of f of g of x by the chain rule is equal to f prime of g of x times g prime of x, right? That's the chain rule. And so f prime, well, e to the x, its derivative is just e to the x again. So you get e to the ln of x. That's this part right over here. This is f prime of g of x. And then this part over here is the derivative of ln of x. That's g prime of x. Okay, so that's what we did on this left-hand side. We used the chain rule. Okay. So this looks a little bit worse, but now everything's going to simplify, right? Because what do we get here? Well, e to the ln of x, we already know that e to the ln of x is just x, right? They're inverse functions. They cancel each other out. So we get that x times d dx of ln of x is equal to 1. And then we can just isolate d dx on its side. You get that d dx of ln of x is equal to 1 over x. Okay? So this is kind of amazing. This natural logarithm, when you take the derivative, you just get 1 over x. Okay, and it's from this kind of tricky procedure. All right, e to the y equals x. By you have to like set e to the ln of x equal to x, take the derivative of both sides using the chain rule, and then by this trick, you end up being able to isolate what is the derivative of ln of x, and it turns out that it's exactly equal to 1 over x. Okay, so these are our kind of derivative formulas for exponentials and for logarithms. So the derivative of e to the x is e to the x, and the derivative of ln of x is 1 over x. And neither of those could we use any of the rules that we had so far. We had to come up with new ways of evaluating these. All right. Any questions on this procedure?
Yeah, that Obos?
Enoch, yes.
Yeah, it's you getting me?
Yep.
Yeah, what if you are going to have a function like a constant raised to some power of function, for example, if you have y equal a raised to the power x or
Yeah,
a
well,
raised to the power 2,
we'll have that in
where,
two slides. We'll have that in 2 slides. We'll do that. We'll
hello?
do that next.
Okay.
Yeah. Okay. Okay, so the derivative of ln of x is going to be 1 over x. Okay, so these are our formulas, right? We have that the derivative of ln of x is equal to 1 over x. What does that mean, right? This means that the antiderivative of 1 over x is ln of x, right? And this lets us complete the power rule for antidifferentiation. Remember the power rule, right? Antiderivative of x to the n is, well, what do we have? We know that it's 1 over n plus 1 times x to the n plus 1. This is whenever n is not equal to minus 1. But when n is equal to minus 1, that's x to the minus 1 is 1 over x. And so now we've computed what its antiderivative is. It's ln of x. So ln of x is exactly when n is equal to minus 1. So this completes the power rules. It's like, how do you find an antiderivative of 1 over x? You can't use the power rule. That would give you x to the 0 divided by 0. But in fact, you have this other answer, which just is the correct answer, is that the antiderivative of 1 over x is actually just ln of x. Okay, at least for positive x. Okay, so this lets you complete the power rule for antidifferentiation. Okay, antiderivatives for x to the minus 1 that's the same as antiderivative of 1 over x, and that's going to give you ln of x. All right, any questions on that? Okay. So this gives us this nice antiderivative formula that an antiderivative of 1 over x is not is ln of x. Okay. Okay. All right. What's another interpretation of ln of x and of the number e? Well, let me draw a graph. I'm going to draw the graph y equals 1 over x. The graph of y equals 1 over x looks like this, right? I mean, it also has a part in this quadrant, but I'm going to focus on the part in the first quadrant. So this is the graph 1 over x. And I'm going to look at 1 right over here. Now, What happens if I just take some point, I don't know, I call it B. And what's this area equal to? Well, the area is equal, as we've seen, it's the integral from 1 to b of 1 over x dx, right? That just means it's the area under the curve. 1 over x is you evaluate an antiderivative and you then plug that in at b, and then you plug that in at 1 and subtract. So what we've seen is we take an antiderivative, which we know is ln of x, right? This is the antiderivative, right? And we evaluated from 1 to b. And that's going to be ln of b minus ln of 1. But what's ln of 1? Any log of 1 is always 0, right? Because this ln of 1 is equal to 0 because e to the 0 equals 1, right? It's ln, remember, is asking what power do you need to raise e to in order to get a number? So we need to raise e to the 0 in order to get 1. That means ln of 1 is equal to 0. So what this leaves us with is just ln of b. Okay, so the area under the graph of 1 over x between 1 and b is actually just equal to ln of b. This is, let's suppose, b is greater than or equal to 1. Okay. And so that means in particular, if b is equal to e, then the area under the graph from x equals 1 to x equals e is ln of e. What's ln of e? So what's the natural logarithm of e? What power do you have to raise e to get e? Well, ln of e has to be equal to 1, right? Because you raise e to the 1 gives you e, right? So ln of e is saying, what number do I raise e to in order to get e? Well, I have to raise it to the 1 in order to get e. So what that tells me is another way I can think about the number e is the number e is exactly the place to draw this line so that the area under the graph y equals 1 over x is 1. Right? So the area under the graph from x equals 1 to x equals e is exactly going to be 1. So this is another way that you could define e, for instance, if you want to. You could say that e is the number so that if you look at the graph 1 over x and you go from 1 up until e, that area there is equal to 1 unit. Okay. So that is okay. So it's another way of thinking of the number e. You can think of it in this geometric interpretation. It's the number that gives you a certain area under this graph. Questions? Okay. Okay, so now, as Enoch was saying, using what we've already seen, it's not that hard to compute the derivative of a to the x for any positive number a. Okay? And the point here is that we know, right, remember, we know that the derivative of e to the x is equal to e to the x, right? That we know. Okay? So what is a to the x? Well, any number a, you can write it as e to the ln of a. Right? Because what does this ln of a mean? This means the number that you have to raise e to get a, right? Remember, this is just our general formula. X equals e to the ln of x. E and ln are inverse functions, right? So yes, okay, so you could do it with first principles, but I'm actually going to do it using the chain rule, okay? So the problem with first principles is that you're going to need to evaluate one of these limits, this a to the h minus 1 over h, which is not a limit that you're necessarily going to know how to do, right? So, okay, I mean, if you claim that this is what the limit's equal to, then that's fine. But I mean, it's not obvious to me at all that the limit is equal to a to the x ln a here, right? So, but I do know that a is equal to e to the ln of a. So a to the x is equal to e to the ln of a to the x, right? Because this is just a. And with the laws of exponents, that's the same thing as e to the ln of a times x. Right here, this is the law of exponents. Right, law of exponents. If I raise e to a power and then to another power, I multiply the exponents. Right, so this a to the x, I can write it in terms of e. It's just e to the ln of a times x. Okay. So now let's take the derivative using the chain rule. Let's take the derivative using the chain rule now. Okay, so the derivative of a to the x is the derivative of e to the ln of a times x, which we've seen this before. So using the chain rule, it's just going to be, it's e to the something. Think of this as this whole thing is g of x. So it's going to be the derivative of e to the x at g of x. So it's just going to be e to the g of x again. So e to the ln of a times x. This is again still our g of x. And then in the chain rule, we're going to have the derivative. But ln of a is just a constant, right? A is just a constant. So ln of a is just a constant. So the derivative of ln of a times x is just ln of a, right? This here is g prime of x. Right? So this is how you do this derivative using the chain rule. E is raised to some function. The derivative is just e raised to that same function, but then you always have to multiply by the derivative of the function. Okay, and then remember this e to the ln a of x, we've already seen that's just the same thing as a to the x. Okay, so this is equal to a to the x times ln of a. And this is the formula. So for example, the derivative of 2 to the x is equal to 2 to the x times ln of 2. Okay. Derivative of 5 to the x is equal to 5 to the x times ln of 5, etc. Okay. Okay, great. Okay, so for a to the x, it's not exactly just a to the x again, but you get this extra constant factor of ln of a, or the natural log of a. Okay, and you can get this by using the chain rule and rewriting a to the x as something involving e. Somehow this is what you always want to do. You always want to rewrite things so that they involve e or a natural log, because these are the two things that work the best with calculus. They give you the nicest formulas with calculus. Okay, questions? Okay. All right, so let's just do some practice. So let's compute the derivative of e to the 4x squared plus 5. So again, this is just the chain rule. Maybe I should say in general, the derivative, as we've seen, of e to the g of x is just equal to e to the g of x times g prime of x. This is a general formula that comes from the chain rule, right? This just comes from the chain rule. And so what do we get? Okay, so now we get, so the derivative of e to the 4x squared plus 5 is just going to be e to the 4x squared plus 5, and then you have to multiply it by the derivative of 4x squared plus 5, and so that just gives us 8x. Okay, so this example is not so hard. Okay. Questions on this?
What?
Yes, Abraham.
The g prime of x is the derivative of the 4x to the second power, right?
Exactly. So it's exactly, this here is your g of x, and then this here is the g prime of x. Yeah, so it's the whole 4x squared plus 5, but the 5 disappears, so you're left with just 8x. Is that okay?
It's okay.
Okay, good. Other questions? Okay. So this we've kind of already done, but let's just do it one more time. So same thing, but let's compute the derivative of e to the ln x using the chain rule, right? Well, the derivative of e to the ln x, again, is just going to be e to the ln of x times the derivative of ln of x. We've already seen that that's e to the ln of x. The derivative of ln of x is 1 over x. But we know that e and ln cancel out because they're inverse functions. So this becomes x times 1 over x, and this just becomes 1. Right? And the 1 is, that makes sense because remember, e to the ln x from the beginning, this equals x. Right? So the derivative of e to the ln x using a complicated chain rule procedure should be the same thing as just taking the derivative of x using the standard power rule. So we know the derivative of x is 1. And so the derivative of e to the ln x should also be 1. And when you do it correctly using the chain rule, you exactly get that it's equal to 1. Questions? Okay, and the last thing is let's re-verify using L'Hopital's rule that this limit that we talked about back at the beginning is actually true, right? So I told you that the limit as h approaches 0. Sorry, question? So I told you that the limit as h approaches 0 of e to the h minus 1 divided by h is equal to 1, right? So now that we know that the derivative of e to the x is equal to e to the x, we can re-verify this using L'Hopital's rule. Let's remember what that is. We have the limit as h approaches 0, e to the h minus 1 over h. We see that if we just punch in h equals 0, this goes to 1 minus 1, which is 0. And this also goes to 0. So we have 0 over 0, indeterminate. Right? So now instead, what does L'Hopital's rule say? It says take the derivative of the top and the derivative of the bottom. So this is, all right, LH for L'Hopital's rule. So what's the derivative of e to the h minus 1 with respect to h? Well, e to the h is just e to the h. This just goes to e to the h. And this over here, the minus 1 just goes to 0. So you just have e to the h. So sorry, that's the limit as h approaches 0 of e to the h divided by, and now the derivative of the denominator is the derivative of h is just 1, right? Remember L'Hopital's rule says that the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x if you get an indeterminate form. Okay. So this just gives e to the h over 1, and now that's fine. Now I can just punch in 0 for h. This is just going to be equal to e to the x is continuous, so it's just e to the 0 over 1, and that's 1 over 1, and that's 1. Okay, so we've re-verified that limit. Okay, so using L'Hopital's rule now, you can, I wouldn't say it's a proof of this because we needed to use this limit in order to get the derivative formula for e to the x. So it's circular reasoning to say that we can now use that to evaluate this limit. What we can say is that we can use it to verify it, to make sure that we haven't created any problems. But with our formula, it does give us the correct value for this limit. Okay, any questions on this? Okay. So I think that's it. Yeah. So we'll end a little bit early today, partly because I don't have as much energy as usual. So some homework exercises. So the first one, calculate the derivative of x times the natural logarithm of x minus x. For this, you're going to have to use the product rule. Second one is again, calculate the derivative of x cubed plus 2x times e to the x at x equals 1. This is again going to be a case of the product rule. And lastly, give an interpretation of the number e squared in terms of the area under the graph of 1 over x. Okay, so this is maybe a little bit more open-ended, this problem number 3, but what I'm thinking is going back to this slide over here, where we interpreted e as the number so that when you take the x coordinate equal to e over here, this area here is equal to 1. So the question is, what does that mean for e squared? Can you, using the graph 1 over x and using geometry, can you say something about what the number e squared is supposed to be? Okay, so it's kind of an open-ended question, although there is basically a correct answer there. Okay, so these are the homework exercises. And so thank you again for your attention. And next week on April 10th, we're going to discuss improper integrals and limits. And these, let me just tell you what these are supposed to be. These improper integrals and limits are eventually going to be used to talk about probability. That's the application that we're building up to. So maybe you've seen at some point you've seen this normal distribution bell curve, something like this. So we're going to try to talk about this using calculus, and the only way that we're going to be able to do it is to understand what's called an improper integral. What does it mean when we're looking at the area under a curve going off to infinity instead of just in some small part? Okay, so that's going to be the topic for next week. And thank you, as always, for your attention. Okay, so I'm going to turn off the recording.